Good morning, everyone. It's been a long time. I hope you had a great week last week. So starting from today, we are going to talk about transportation problem and assignment problem. And especially for today, I believe we are going to focus on the transportation problem, and probably next time we're going to continue to talk about the assignment problem. And just to let you know, these two problems are prototype of the linear programming problem. So if you look at any operations research textbook, then you're going to see both problems as for sure. Okay. So the transportation problem received this name because many of these real-world applications involves determining how to optimally transport the final goods, final product. However, I should mention that some of these important applications actually have nothing to do with the transportation. Okay? So later today, I'm going to give you one example that just shows something like that. Okay, so this picture shows a prototype transportation problem with three sources, 3 supply nodes, and 4 destinations. Those are the demand nodes for the flow, and with the associated shipping costs. And the goal of the transportation problem is to find the least cost way of transporting goods from sources to destinations. And while at the same time satisfying the customer demands. Okay, of course, without exceeding the available supply amount. Sorry. Okay, so let's consider a similar example with the same number of sources and destinations for the flow, for the transportation problem. So basically this network diagram on the graph shows the shipping cost and supply and demand for a power company, right? And the power company has the 3 electric power plants that supply the needs of those 4 different cities. And for example, power plant number 1 can supply 35 million kilowatts per hour, and power plant number 2, in this case, can supply 50 million kilowatts per hour. And let's say the peak demand, peak power demands in city number 1, which occurs at the same time, is 45 million kilowatt. In city number 2, it is going to be 20 million kilowatts, and so on. Okay. And the cost of sending the 1 million kilowatt of the electricity from plant to each city depends on the distance. So the electricity must travel. So those are the shipping costs. And given the information, I can make a nice parameter table like this, which summarize all of the critical information. So this table, I have listed sources in each row and destination in each column, right? And it also includes the shipping cost from each source to the destination, and the customer demand, the available supply amount for the power company. Okay. So again, our goal is to find the least cost shipments that can satisfy the given requirements using the available supply amount. Okay. That's what you are going to do with the transportation problem. So obviously, obviously these are the one of the optimization problems, right? An optimization problem is a computational problem where the objective is to find the best of all the possible solutions. So when you deal with it, first you need to define the problem of interest. And once the optimization problem is defined in words, the very next step is to reformulate this problem in a form that is convenient for the analysis. Okay, and the conventional operations research approach for doing this is to construct a mathematical model that represents the essence of the problems. Okay, we've been discussing the mathematical model consists of a decision variable, objective function, and some constraints, right? And we've already learned about the LP, linear programming model. So typically, the linear programming model is a mathematical model where both objective function and constraints functions are the linear functions, right? And so the decision variable is the number of variables plus values will be determined, right? So basically, this is what you want to know, what you must be determined within the model along the way to determining what you really want to know, right? So in our case, we could define a decision variable. So for each decision that the power company must take, right? So because the power company have to determine how much power is sent from each plant to each city, we define the decision variable X by J is the number of the million kilowatts produced at plant number I and sent to city number J. And the objective function is the measure of performance expressed as a function of the decision variable, right? So this is what you want to either maximize or minimize, right? So in our case, it's going to be the minimizing the total shipping cost, right? Or minimizing the total travel distance, something like that, right? So so the cost of supplying the peak power demands from, for example, plant number 1 to each city is going to be 8 times X11 plus 6 times X12, 10 times X13 plus 9 times X14, right? So the total cost of supplying the peak power demands for each city maybe you need to add 2 more things, right? So it's like the 9 times X21 and 12 times X22 and 13 times X23, 7 times X34. And also you need to add the 14 times X31, 9 times X32, 16 times X33, 5 times X34. And the constraint sets, right? So in our case, the power company faces 2 types of constraints. The first one is the total power supplied by each plant cannot exceed the plant's capacity. That is what it calls supply constraint. So for example, the total amount of power sent from plant number 1 to the 4 different cities cannot exceed the plant number 1's capacity, which is in this case 35 billion kilowatts, right? So that's why we can have the first supply constraint. looks like this. And in a similar way, we can find another constraint for plant number 2. That's going to be x21 plus x22 plus x23 plus x24 is less than or equal to 50 million kilowatt. So similar way, you can have another constraint for plant number 3. That's going to be x31 plus 32 plus 33 plus 34 has to be less than or equal to 40. So we have 3 supply constraints, right? Because there are 3 sources in this case. So next set of constraint is what we call the demand constraint. So in this case, we need to ensure that each city will receive sufficient amount of power to meet its peak demand, right? Because each city demands power, each is a demand point, right? So for example, for city number 1, city number 1 must receive at least 45 million kilowatt. So we obtain this constraint. X11 plus X21 plus X31 has to be at least 45 million kilowatt, right? That's for the demand constraint for city number 1. So similarly, we can obtain another constraint for each of cities 2, 3, and 4, right? So for city number 2, it's going to be x12 plus x22 plus x32, right? Has to be greater than or equal to 20 million kilowatt. Right? Likewise, for city number 3, it's going to be x13 plus x23 plus x33 has to be greater than or equal to 30. So you need to add one more constraint for city number 4. So you're going to have 4 different demand constraints, one for each city, right? So we call this demand constraint because these constraints ensure that location, city, each city receives this demand. Okay? And also because all of the x variables, the decision variables must be negative, we add the sign restrictions. So combining all together, objective function, supply, demand constraint, and sign restriction. There's this LP formulation. And using Lindo or Lingo, you can solve this transportation problem. And actually, there is a streamlined version of the simplex algorithm for the transportation problem, but we are not going to talk about this. So, in general, transportation problem is specified using this notation and general formulation of the transportation problem is just like this. Okay. So keep in mind that the transportation problem deals with 2 sets of the constraints, supply constraint and the demand constraint, besides the restrictions. Okay, so why don't you take an example? I got this example from our textbook. So the Child Fair company has 3 plants producing child pushchairs that are to be shipped to 4 distribution centers. And plants 1 to 3 produce 12, 17, and 11 shipments per month, respectively. And each distribution center needs to receive 10 shipments per month. And the distance from each plant to the respective distributing center is given. And the freight cost for each shipment is $100 plus 50 cents per mile. And how much should be shipped from each plant to each of the distribution centers to minimize the total shipping cost? So let's formulate this problem as a transportation problem. And so I do recommend you to construct the appropriate parameter table. Okay. So let me give you like 1 or 2 minutes. Why don't you construct the parameter table for the transportation problem? So we can consider this as resources, right? This is source. And this is going to be our destinations, right? For destinations. So we have 3 sources, 3 different plants, and 4 destinations, 4 different distribution centers, right? And so how's the supply amount? Here? Or let's get the table right here. And one. Distribution center. Just make the Sorry.
Maybe just abbreviate distribution center to DC.
Okay, DC. Okay, thank you. 1, 2, 4. So, what number you're gonna put them in here?
I would actually put it the actual cost.
Right, actual cost. So right here, it's not gonna be 800, right?
It's going to be $740.
740.
Yes, sir.
Okay.
The freight cost per shipment.
Okay, so here. So I just say this is going to be C sub 1. Always it goes by the row number first and the column number. Okay, so how'd you get the value of C11?
Put $100 plus 0.5 times 800 miles.
Okay, great. Because in here, the freight cost for each shipment is $100 plus 50 cents per mile, right? And we know that from this given table, the distance from plant number 1 to distribution center is 800 miles. So what you need is $100 plus the total distance, which is 800 miles times 50 cents per mile, right? So 0.1. So how much is that?
740.
Really?
Yes.
So 100 plus
800 times.
400.
Wait, oh, it's times 0.5,
Yeah,
not 0.8.
it's
Sorry.
0. This is going to be 500, right?
Yeah, sorry about that.
No problem. At least you got the right formulation, right? Right. But simple calculation mistakes. So we have 500 here. Okay. We're gonna put the number 500. Then how about C sub 1, 2? How do you get this number? So similarly, C sub 1, 2 gonna be 100 plus travel distance, which is 1300 times 0.5, right? How much is that?
750.
750. This number 750 goes in here. Okay. So similarly, how much do you have this? 100 times 100 plus 400 times 0.5.
300.
That's going to be 300. How about here?
That's going to be
400. Okay, let's move on to the second row. So similarly, you should be able to get all of these 8 different values, right? So we always 100 plus whatever the travel distance from each plant to the distribution center times 50 cents. That's what you need to do. So I believe this is going to be 650. And this is going to be 800. And this is going to be 400. This is going to be 600. Yes, sir. keep going, then that's going to be 400. So this 100 plus 1200 times 0.5. So that's going to be 700. Next one should be 500, right? So, right?
And 500.
500.
Yeah, it's correct.
Right, yeah. 100 plus 900 times 0.5. Yeah, 500. That's right. Okay, so now next, what you're gonna do is put the demand amount. Or let me just use capital D. Capital D stands for the demand amount at each distribution center. Okay, that's gonna be minimum requirement, right? That's gonna be, how much is that? So here, let's say each distribution center needs to receive 10 shipments per month, right? So we're gonna have 10. Right? For each distribution center, demand amount is 10. How about the supply amount?
That would be 12, 17, and 11.
Yes, that's correct. So from here, let's say plants 1 to 3 produce 12, 17, and 11 shipments per month, respectively. That's gonna be our maximum supply amount, right? 12, 17. Now, based on this, you should be able to get the transportation cost. Okay. So this is the supply constraint and demand constraint. You already know the supply amount and demand amount, and also the cost values, right? So you should be able to get this. Okay, so next thing, what you're going to do is, why don't you open up Window or Lingo using the computer in front of you, and then plug in the transportation problem linear formulation, and run it and get the solution. You know, okay? That's my Window screen. So you can also use Lingo if you want, but I'm using Lingo format. Remember, if you want to use Lingo, then what you need is to go to options, right? And you can choose window. Try. Okay. Have to open the new window. Make sure you can see the window. But I'm using window for like this. You can choose back and picking the first option. Okay. And then you have window.
So
Yes.
to punch in for your, is there a chance you could please move your window a little bit so I can see what you're typing in when you're putting in the constraints. Did you type in subject to the ST?
No, for Lingo, we do not need subject, right?
Oh.
Or ST. For Lingo, you do need ST or subjective, but for Lingo, you shouldn't put those, right? After you input your objective function, make sure you're gonna end your objective function with semicolon. Right after that, just type in your constraint one by one.
Okay, thank you.
So I got the optimal solution. Objective function value is 20,200. And these are the optimal solution. Just make sure and you also have the same solution.
Could you please minimize your solution report so I can see
Okay.
what you put in? Yes. Okay.
So this is for Lingo. So let me give you the one for Lingo. Share. So I got the same solution, similar solution from Lingo and Lingo. This is for Lingo. Down here, this is the for Lingo.
I think I got something else.
You got something else?
No, I think I don't know if I'm doing it wrong, but it keeps telling me about feasible solution. I don't know.
That will be also used. This. Where this is the three.
Oh,
So, and then, yeah.
other,
Okay. So
okay, yeah, okay, thank you.
no problem. So it looks like without having the ending mark, the window for Lingo can be used as a solution. You don't have any.
Oh, yeah, I don't. What is the ending mark? Oh, just, did you say end?
So
Oh, yeah.
it looks like
Okay,
it's
I don't
working.
know.
Okay. Okay, by the way, was you, I know you pick up the teachers. Did you?
Well, I have to get
Yeah. But it's come down. Yeah, right at the class. Yeah, but it's still running. You double check your objective coefficient values.
Oh, 650 here.
Okay.
400, 600.
Is there?
Ah,
Should be
that's
okay.
thank you.
Okay, so it's like everyone that the optimal solution. Okay, so any questions on this example? it's pretty straightforward, right? Yes. But now you
The key is
need
just to make sure you punch it into Lindo or Lingo the right way.
to. That's true. And also in this case, well, this is, I'd say, it's not a tricky part, but somehow you need to work on how to get this closed table, right? That's the key thing. in this example. Okay, so let's move on to the next example problem. Okay, so let me read the problem description first. So bank has two sites at each checks are processed. And site number one can process 9,000 checks per day, and site number two can process 7,000 checks per day. The bank processes the three types of checks. Each day, 5,000 checks of each type must be processed. The processing cost per check depends on the site at which the check is processed. And you are required to determine the linear programming model to minimize the daily cost of processing checks. Okay. So although many applications of the transportation problem get involved with determining how to optimally transporting the final goods, some of its important applications actually have nothing to do with the transportation. So this is one of those examples, okay? But I believe you still can borrow the formulations of the transportation problem to this problem, okay? So let me give you a couple of minutes. Why don't you complete the parameter table for the transportation problem? After that, you should be able to get the constructed transportation LP model. Okay.
So when it says like 5 cents, is that like per check?
Mhm. Okay, so in this case, you may consider the these two processing sites as the sources. Okay, and the check types to be the destination, or vice versa, right? Either way should work. So
I actually did the sites as the sources and the checks as the destination. How do you do it?
okay,
Sites and sources, yeah, I was doing that as
Okay,
sources.
then let's do this. In our transportation model, the processing size as the sources and the check types as the destination. But like I said, the different way should work, other way should work. Okay. So
Would you like to load it into Excel? You know, you can pull up an Excel sheet and then we can type the whole thing as the tab level, so you don't have to use the mouse.
oh, that's good. That's good. Yeah. But here I just need to write down these several different numbers. But yeah, let me do that from next time. But that's a good idea. Oh, I never think about that. Yeah, that's really good. So here, you know, what is that? 9,000 goes here.
7,000.
7,000. And what about
Demand is just 5,000 for each.
5,000? And you can actually use these 6 numbers, right? You need other computation, right? So I believe we already get the complete table, right?
So like you can put the actual amounts.
Mhm.
Would that be okay?
Yeah.
Because all I do is I multiply each of the amounts by 9,000 each to get the total cost to run the thing.
Yeah, I just left it as percents.
And you say I was confused about that. Should you just leave it as cents?
Yeah, it's the sense.
Oh,
So we can use these numbers. These are the my cursor. And let's work on window or lingo. Okay, to get the optimal solution.
Yeah, window seems like it makes more sense.
Did you already got the solution? I got 45,000.
I got the, oh yeah, sorry, I put the amount in dollars. So
Okay.
because that's 45,000 cents.
Okay, yeah, 45,000 cents. That's
Yeah.
right. I think there's one. Because you got the same X variable values.
4,000, 5,000, 5,000, 5,000. Yes,
Okay.
sir.
Let me do this one more time with window. We'll copy everything, paste. Just remove the asterisk symbol. Remove the semicolon. Constraint. And put the subjective. Okay. Any questions?
Sure.
Is that good?
Just have to load it into the Tableau and use it that way. And then make sure that we have the Tableaus right and then plug it in. So it should be too bad.
Okay. Okay, sounds good. Okay, so this is all for today. And next time, we are going to talk about the assignment problem. That's going to be another prototype of the linear programming model. It's going to be very similar format, but I'm going to introduce some specialized algorithm for solving the assignment problem, which is called Hungarian algorithm. Yeah, Hungarian. Okay, thank you. So see you next time.
Thank you.
Share my screen. Already.
Thank you so much. Sir.
Was he sharing screen?
Yeah, you were.
Oh, really?
You got it.
Okay.
Oh.
Thank you.
That's good.
Oh, yeah. Oh, yeah. I did.
So you're not record the whole thing. Over again.
And I
Oh. Yeah, yours.